Welcome to the deep dive into this module called PySCF, or Python Self-Consistent Field. And that doesn't make a whole lot of sense until you say it computes numbers that define the Hamiltonian. It doesn't solve the whole Hamiltonian, but it computes numbers particularly from integrals. And one of the functions that performs this action is the integral operator request routine. And the different integral that it can evaluate are the one electron integral kinetic term, the one electron integral nuclear attraction term, the 2 electron integral, which is the electron repulsion term, and this is the one that takes a lot of calculations. That's the most complicated of all the things up here. Sometimes we'll see the suffix called SPH, and that stands for spherical, and it's the coordinate orbitals versus Cartesian. In other words, it's based on a radii and angles rather than XYZ coordinates. Now, we'll see these things in the code as we step into the code and identify different pieces. So when you see those, this is a reminder to me and a reminder to you what those abbreviations are representing. Video 12 ran this program H2 Energy's final. Layer 1 was just the molecule definition in geometry, where we have the distances between the nuclear centers, and I'm really not going to focus on this. There's no deep dive really necessary in that area. Here's our focus, is to calculate the integrals, which we called H, PQ, and G, PQRS, if you remember that. If you don't, then you probably need to go back on the videos that actually talk about those integrals. Here's our special driver, and here's the abbreviation, this Python self-consistent field. And as you can see here, the atom is defined here with one hydrogen at 0, 0, 0 and the other hydrogen at 0, 0 and some distance, 0.575 all the way up to 2, which is what we showed in the last video. Now, this first hit here is so that we set things up ready to run, and then we actually run the thing. And what we're going to do is step into the code that involves some of these imported Qiskit routines that really do all the work. This thing is real simple because it uses those items that solve everything for us. So let's get started, and I'm going to run the program. And I've got these breakpoints set so we can see what's going on. Here we are. Now, this driver.run, notice this establishes the driver. It has all the parameters that we need to calculate this particular molecule with its distances. And here's the driver, and we're actually going to run the driver. This defines the driver, and this runs it. So let's step into the code and see what we find. Okay, here we are. This is our first breakpoint, and we've got this run the PySCF, the Python self-consistent field routine. So let's keep going and step into this routine. Now we're up to a place where it says build the molecule. That's another function. So let's step into what that thing's doing. Here's the return val setting up for that. There's the molecule format that we set earlier. Now we talk about something where we're talking about the kinetic term. You can see how all these different things get involved. Here you can see we're making a decision here about whether we want to use the one electron nuclear integral or not, or the nuclear term within the Hamiltonian. Another reference to the kinetic term. Here's one's kind of interesting. Here we've got the Hamiltonian and the electron energy from raw integrals, and here's the integrals, Hij, Hij_KL, and I think we're just about to finish up on our integral calculations. And there we are, ready for the Hamiltonian, using the annihilation and creation operators. So that's just touched on some things, and just to give you an idea what the internals are like and how all that stuff takes place. Now it's interesting to keep in mind that this does not require a quantum computer. This stuff is just done regular whether we're tied to a quantum computer or not. And that gets involved farther down here where we map the qubits to the fermions.